Like all other derivatives, amides are named as if they were carboxylic acids first. So starting at the carbonyl, counting 1, 2, 3, 4, 5, 6 carbons. 6-carbon IUPAC name would be hexanoic acid. Hexanoic acid becomes hexanamide when you realize that it's an amide over here. There are things dangling off of this amide. Here's one. There's two. So if you were naming it as the carboxylic acid, it would be 4,4, 1, 2, 3, 4, 4,4-dimethyl hexanoic acid. But again, realizing it's an amide, it's a 4,4-dimethyl hexanamide. But wait, there's a carbon group on my nitrogen over here, and that has to be named also. So it becomes N,4,4-trimethyl hexanamide. Yep. All right, over here is a cyclic amide. Cyclic amides are called lactams. So this, if we do common name, this is a lactam. It's a 1, 2, 3, 4, 5 carbon in total lactam. So it becomes valorolactam, since valeric acid is the common name for a 5-carbon acid. Using common nomenclature says the carbon next to the carbonyl is alpha. The carbon next to that is beta. So this is beta valorolactam. IUPAC naming is similar to naming cyclic esters. You name the root name is the total number of members in the ring. So it's a cyclobutane. You have to acknowledge there's a COO carbonyl on one of the carbons. That's actually carbon 1. So it's a cyclobutanone. You recognize the 2 spot is not a carbon, but a nitrogen. And when we named esters, we named it an oxo. But this is an AZA, AZA. So it's 2-aza cyclobutanone. There's another thing hanging off of our aza cyclobutanone. It's on the 3 carbon and it's an ethyl. So the full name is 3-ethyl 2-aza cyclobutanone. There are a few more amide naming examples for your viewing pleasure. We won't really talk through them, but one thing I wanted to point out and make sure you're aware of is if there is a leg on your nitrogen of your amide, you have to name it as an N-substituted derivative. If there are 2 legs, you must name both of them as N-substituted things. They could be different, they could be the same. Make sure you name the legs on the nitrogens of your amides. Here are a few more examples of lactams that you can practice on your own if you wish, but I'm tired of nomenclature already. So, moving on to reactions that amides do. Amides are low on the totem pole of reactivity, so there's not a lot that they do. In fact, these reactions are almost all that they do. Let's draw a mechanism for that first one. All right, mechanism for that first reaction of an amide. Hopefully you already know what the name of this reaction is. It's got acid, and water. It's the type of reaction that all carboxylic acid derivatives have in common. That's your hint. We've seen previously when we have acid and a carbonyl, the first thing we do is protonate the carbonyl oxygen. And then attack the carbonyl carbon. Amides are not very reactive. They need to be catalyzed by something like acid or base. So we got here, like all the others, when you get here and your nucleophile that just attacked is positively charged, clean up, everybody clean up. Hopefully this is familiar. It's a neutral, tetrahedral, intermediate. From here, we're gonna want something to go away, but nothing can go away from this neutral intermediate, because if I lost this, I would be losing an N minus. If I lost this, I'd be losing an O minus, carbon minus. We don't like any of that, especially when the reaction is catalyzed by acid. So we need to protonate our leaving group before it leaves. Who's my leaving group? Well, this is hydrolysis of an amide. So what hydrolysis means is I'm going to cut the bond between the carbonyl and the neighboring atom, whatever that atom may be. So my nitrogen is actually my leaving group. Protonate the leaving group. Now that I've got a positive leaving group, I'm ready to fold down and kick it out. Almost time for ta-da, but not yet. When I just kicked out my leaving group, I kicked it out as a neutral nitrogen. I made an amine in solution after it left. I still have a positive charge on this piece over here. The amine is the base that's going to come clean that up. So I end up here. Note, carboxylic acids, because they're acids, the pH is frequently a consideration in reactions like this. So in a reaction that's catalyzed by acid, we're going to assume it's a large concentration of strong acid. We're going to assume it's probably a pH of 3, maybe even less. But we're going to assume it's a pretty low pH. So I made you memorize 2 pKa's back in the day. As it turns out, you memorized these 2 pKa's back in the day. That will be quite relevant this lesson. This is a carboxylic acid. It has a pKa of around 5. I hope you knew that. This is an ammonium ion. Disclaimer, it's actually an aniline ion because it's benzene, but my explanation here applies whether it's an aniline or ammonium, regardless. It's an ammonium ion, and we memorized that that has a pK of around 10. Again, because it's an aniline, it's a little bit of an outlier pKa-wise, but the information still applies. So at a pH of 3, that's below the pKa of an ammonium, and that's below the pKa of a carboxylic acid. What that means is both products with an H. That means both products have an extra H plus at that pH because they are below the pKa. We're finished. These are our products. But wait, no, we aren't. If you look back at your PowerPoint, after the acid and water stuff, sodium hydroxide was added to the mixture. So acid and water did all the stuff up to this point, but then sodium hydroxide is added to the mixture. What's the sodium hydroxide there for? It's to help neutralize each of your components. Sodium hydroxide is going to take an H from him and an H from him. Let's do it. Oh, lied. An H2 and another hydroxide molecule is going to take an H from your carboxylic acid. O minus. So a thing of note, when sodium hydroxide or another strong base is listed in this carboxylic acid section, we have to associate that to a pKa, or pH, I'm sorry. pH of this solution, because it's basic, we're going to assume is probably around 12. So bases make your pH of your solution high. When we see sodium hydroxide as a reactant, we're going to assume it's a pretty high reaction, a pretty high pH, dang it. So since this guy is already here, we know his pKa is 10 as an acid. So he must become his basic form after you add sodium hydroxide. We know his pKa is 5, so he must become his basic form when you're at a pH above the pKa. The pH is greater than the pKa for both of these things at this point, so both of them lose an H. Students are not always confident and comfortable with pH and pKa discussion. If I have a pH of 7, does that change both the ammonium and the carboxylic acid? If I were to have some sort of solution that said, maybe I add water, and adding water assumes a neutral pH of about 7. There are 3 pH ranges we will see in this unit. Acid means about 3. Base means about 12. And water means about 7. You need to know how the identity of these, what the identity of these will be at pH 7. Yep, acids and bases, man, it's a big deal. Okay, one more thing about this, and then we're going back to the PowerPoint. Why do I care? Why did I not stop here after acid was added? Why did I go one step further? Well, the true reason is so that I could explain how this happens, why this works. But why would someone maybe want these products versus maybe someone want those products? If you remember way back in the day when we first did something like an acid-base extraction, sometimes you want a certain thing to be soluble somewhere, so you've got to change whether it's protonated or not to make it soluble or not. Heads up, the bottom reaction is the other reaction of amides that we will focus on. Have you seen P2O5 recently? Have you seen it as a reagent ever before? We previously said it's a useful but not required reagent for fill in the blank. It's a dehydrating agent. Yep, dehydrating, as in losing water. 2 H's, 1 O. We lose water here. So if you lose 2 H's and 1 O, you end up with a C and an N as the only things that are left. You make a nitrile. So amides can be hydrolyzed, amides can be dehydrated to form a nitrile. Note, this is not any old amide. This guy, not any old amide. It has to be an amide that has 2 hydrogens on this nitrogen leg. If there are not 2 hydrogens there, you cannot lose water, so you cannot do a dehydration. There could be anything on this side over here. What's on this carbon doesn't matter. But the amide itself, that nitrogen has to have 2 hydrogens in order to do this dehydration. Amides can be hydrolyzed. Amides can be dehydrated to form a nitrile if it's that certain kind of amide. Amides are also important when talking about amino acids. But does an amino acid have an amide bond? No, absolutely not. However, when amino acids connect together to make proteins and peptides, absolutely, there's an amide bond connecting those things together. So let's look at our amino acids. This is an L amino acid. Why is it L? Because when I draw this amino acid in a Fisher projection with the carboxylic acid up top and the nitrogen and hydrogen along the middle, your amine along the middle, the horizontal, and your side chain of your amino acid dangling down at the bottom, my amine, my nitrogen, is on the left of my Fisher projection. So I know that it's an L amino acid. So what's the difference in all these structures of amino acids? They're all in different protonation states. Because there are 2 functional groups to be concerned about when you're talking about amino acids, we have to know the pKa of 2 functional groups. The same 2 functional groups we just talked about on paper before we came back to the notes. Ammonium ions have a pKa of around 10, and carboxylic acids have a pKa of around 5. So we're going to talk about these functional groups at 3 different pHs. pH 3, pH 7, pH 10. Anytime the pH of a solution is above the pKa of the thing in question, your thing in question will be in its basic form. Anytime the pH is above the pKa of the thing in question, the thing in question will be in its basic form. Anytime the pH of a solution is less than the pKa of a thing in question, the thing in question will be in its acidic form. So when we talk about pKa's, we're talking about the acidic form of the thing in question. So ammonium ions that have a pKa of 10, that tells you it's in its acidic form everywhere below 10, and above 10, it loses an H. Carboxylic acids have a pKa of 5. Everywhere below a pH of 5, it's in its acidic form. Above 5, it loses an H. So there's a picture of an amino acid here that's a pH 3. So you're below the pKa of both groups. Both should have an H. Ding, ding, it's that one. At a pH of 12, you're above the pKa of both species, so both should be without an H. Ding ding, it's that one. What happens when you straddle the pKa's? When you're at a pH of 7, 7 is above 5, so the carboxylic acid will be a carboxylate. 7 is below 10, so the ammonium ion will be with an H. This guy up here is my pH 7 version. It's confusing, I know, but it matters, unfortunately. All right. Why does it matter so much? Well, one reason it matters is because peptides can be sequenced using reactions that we are now all familiar with. If I take this very deactivated benzene derivative, I can do a reaction with this peptide. This very deactivated benzene, really good at nucleophilic aromatic substitution through a Mesenheimer intermediate. Oh my God, yeah, for real. This guy, good at substitution through a Mesenheimer intermediate. So the nucleophile that's going to attack from this peptide is the N-terminus. The N-terminus is your nucleophile, no matter what peptide is in question. So you hook those guys up and then you hydrolyze the peptide to figure out which peptide, which amino acid has this whole benzene derivative on it. And that tells you that that amino acid was the N-terminus of your peptide. Kind of cool. There's a lot more sophisticated ways to do this, but this is a wet chemistry way to sequence a peptide. One more thing of note, you can do complete hydrolysis, which chops the peptide into tons of pieces, breaks every single carboxylic acid derivative bond, or you could do partial hydrolysis, and partial hydrolysis will cleave the most reactive carboxylic acid derivatives more easily, so you can cleave only parts of the molecule and leave parts of the structure intact. Let's see what the heck we're talking about by hydrolyzing that peptide and, yep, drawing bunches of big products. I cheated and drew most of the peptide off camera, but if you'll notice, one thing that I didn't draw is 2 H's on this terminal nitrogen, my N-terminus of my peptide, because it's that N-terminus that adds to, does the nucleophilic aromatic substitution with my very deactivated benzene that we just saw. So when I do the nucleophilic aromatic substitution reaction, here's what I get. Ta-da! That's great and really exciting, right? Why? What was the purpose of doing that reaction? So that then I can hydrolyze this thing and get multiple products, detect which amino acid has the very deactivated benzene connected to it, and then I know by identifying who's connected to the very deactivated benzene, I know who my N-terminus was. It's a sequencing process. So I'm going to hydrolyze this. I'm going to hydrolyze this with sulfuric acid, water, and high heat. I'm going to heat it a lot. I'm going to heat it for maybe 24 hours so that I can make sure I completely hydrolyze this peptide entirely. It's a peptide, It's got a bunch of carboxylic acid derivatives. It's got a bunch of amide bonds. We're going to hydrolyze every amide bond. Is this an amide? Amide, we're going to hydrolyze this one. Amide, we're going to hydrolyze this one. Amide, we're going to hydrolyze this one. And officially, this is a carboxylic acid, so that thing could be hydrolyzed. That thing could exchange if we were doing like isotopic labeling or something. You could exchange that thing too. So I'm going to pause for a second while I draw all of this. Nah, I'll bring you with me. It's okay. You can watch me draw slowly. I'm leaving no connection to anything where I chopped that piece off. Everywhere I chopped a piece, I'm leaving nothing. I'm not replacing that bond with anything thus far. So there are all my pieces drawn out with simply erasing the bond that used to be an amide bond or a carboxylic acid bond. So then I have to think, if I'm hydrolyzing an amide, what used to be the carbonyl of my amide now becomes a carboxylic acid. But wait, because I'm creating a carboxylic acid, which is an acid, I have to double check my conditions to decide what's the pH of this solution, what's the probable pH of the solution. So with a low pH, should that carboxylic acid be with an H, without an H? With an H. When I hydrolyze my amide, I'm going to kick out an amine, an NH2 amine. But wait, I need to check my conditions to check my protonation state. I'm at a pH below the pKa of my functional group in question. So I add another H to the mixture to make it positively charged. So where I hydrolyze my amides, my carbonyl is going to become a carboxylic acid with an H, and my nitrogen from my amide is going to become an ammonium ion, a positively charged nitrogen with an H. That happens everywhere you cut things. The carbonyl becomes an OH. The amine, the nitrogen, becomes an ammonium. The carbonyl becomes an OH. The nitrogen becomes an ammonium. The carbonyl becomes an OH. My OH better not be an OH minus. It will make water, but because I'm in acid, it will probably regenerate some hydronium. Water or hydronium would be acceptable here, but the truth is it doesn't have a carbon, so you don't have to draw it. Who cares? I'm just telling you that that would probably be hydrolyzed. Some exchange would go on between your solvent stuff and your carboxylic acid from your original carboxy end of your peptide. Okay, great. That's good. So what? Well, then you go through a process of identifying which amino acid has the very deactivated benzene on it. Well, that's this one, of course, and that's alanine. So you know that alanine was the N-terminus of your peptide. Whew. It would be great if that were the end, but wait, there's more. What if I hadn't hydrolyzed it in acid? What if I hydrolyzed it in base? What does that change about what products I get? If I hydrolyze this guy with sodium hydroxide and water, and I'm probably going to heat it again, I'm going to hydrolyze every amide bond just like before. So I really am going to cut out this time so you don't have to watch me slowly draw. All right, here's the same sort of situation where we started previously, where I broke the amide bonds, but I did not replace that bond with anything. The carbonyl carbon will always become a carboxylic acid in hydrolysis, except when you're in base, you're assuming a pH of a solution of about 12, and a pH of 12 is above the pKa of a carboxylic acid, so you really get a carboxylate. The hydrolysis of the nitrogen part will always result in an amine or ammonium ion. At a pH of 12, you're above the pKa, so it's a neutral amine, NH2. Neutral amine, NH2. Neutral amine, NH2. Carboxylate, carboxylate, carboxylate. This one could technically be hydroxide, or it may be a water. It just kind of depends a little bit. But again, same as before, I just wanted to point out that you could hydrolyze that carboxylate. It may simply undergo a deprotonation instead. There is one tricky little thing here. Because you're using a certain amino acid, because your peptide contains a certain amino acid, this phenol, which has a pKa of 10, this phenol will also get deprotonated if you hydrolyze this thing in base. Beware of reactions on the side chains of your amino acids. That's enough for now. Nitriles next time.